last talk so we can take a couple of screenshots of all of your faces or icons or however you prefer. That would be wonderful. So Nikhil, whenever you're ready.
Okay, so thanks everybody for sticking around. So previously, before the break, I showed you this theorem S, which says if you have a generalized adjacency matrix for a graph with a spectral gap and a positive top eigenvector, which Cynthia pointed out, then you get this nice diameter bound. And now I'm going to show you how to apply this to polytopes. So let's go back to setting a polytope. So I have a polytope P given by some AX less than or equal to B, where none of the constraints are redundant, and B is positive. And so it has M facets, that's equal to the number of constraints. And it has some N vertices, and we don't know what that is. It could be some very large number. And two vertices are, okay, we're interested in this graph GP, which is the adjacency graph of vertices in this polytope, where adjacency means that they are the endpoints of an edge in the polytope. So in order to apply theorem S, we're actually not going to work with P. It's going to be important to work with the polar of P. So recall that if you have a polytope P, a bounded polytope in RD containing the origin, its polar is another polytope in RD, which is actually just the convex hull of the constraints, appropriately constraint vectors A1 through AM, appropriately normalized by the BIs, which are positive. So this makes sense. So this is another polytope in RD called P polar. And this has very nice properties. So in particular, the vertices of the original polytope correspond to facets of the polar. And the facets of the original polytope correspond to vertices of the polar. Okay. Yeah, sorry, I should have written, right. So the, maybe I should draw, right. So the facets of the original polytope correspond to vertices of polar, and the vertices of the original polytope correspond to facets of the polar. So maybe a standard example, on the left, you have the L infinity ball, the hypercube in RD, which is P, and its polar is just the L1 ball. And so the vertices are these red dots, and they correspond to the codimension 1 facets of P polar on the right-hand side. And now the nice thing about the polar is that adjacency of vertices in P corresponds to adjacency of facets in P polar. Okay, so if you have vertices V1 through Vn, they correspond to some facets F1 through Fn. And the point is that two vertices Vi and Vj are incident in P in the original polytope, if and only if the corresponding facets intersect in the polar. So what that means is that this one skeleton of the original graph is actually literally equal to the facet incidence graph of the polar. So any questions about this? Okay, so in particular, if I bound the diameter of the facet incidence graph of the polar, I'm happy, right? Okay, so this is now our goal, right? You have P, we pass to P polar, which now has N facets. So it should be a capital N. And the goal is bound the diameter of the facet incidence graph of P polar. Okay, so the key idea in this is to do something that seems a little bit not like irrelevant, which is to look at the volume of P polar. Okay, so this is the key idea. So I'm going to write P polar as mx less than or equal to C naught, where M is some matrix. It's going to be N by D. So it's not the same as A. It's not the same dimensions as A. And some vector C naught, where C naught is, let's say, positive. And no redundant constraints here either. So I can write P polar in this way because I can write any bounded I can write any polytope in this way. And now the key idea is to consider the volume of P polar as a function of the slack vector C. Okay, so this is defined by a bunch of linear inequalities where the right-hand side is given by C naught. I'm now going to treat that C naught as a variable and look at P polar of C, which is going to be now a polytope where the right-hand side is replaced by the vector C. So that's a bounded polytope that has some volume. And so I'm going to define this function V of C, volume of P polar of C. It's well defined in a neighborhood of C naught. It may not be defined everywhere because, you could, well, I mean, you could just get, well, okay. It could be defined anywhere, but you might get something empty. But let's just look at it in a neighborhood of C naught. Okay, so any questions about the definition of this function? Okay. Okay, so this function has two nice properties, which are both classical, maybe known for close to 100 years. And let me tell you what they are. So these properties require a non-degeneracy assumption, which is that P polar is simple, which we'll remove later. So don't worry about it. That's just a technical assumption if you know what it is. So if P polar is simple, then it turns out this function is differentiable. It's actually twice differentiable, this volume function, at least locally. And the first claim is that the Hessian of this function is a generalized adjacency matrix of the skeleton of the polytope, of P, which is the facet incidence graph of the polytope. Okay, so this makes sense, right? Because P polar has n facets, which is the same as the number of vertices of P. Now, this function is a function of n variables, right? Because for each facet, I can change the slack in that facet. And so the Hessian is an n by n matrix indexed by the facets of P polar. And so this statement at least makes sense. The Hessian of V is a generalized adjacency matrix of P, of GP, which is the facet incidence graph of P polar. I'll prove this in the next slide, but any questions about the statement? Okay, so this is like a combinatorial property of the Hessian, saying that the pattern of non-zeros in the Hessian is related to the underlying combinatorics. This, I guess, goes back to at least Alexandrov, but maybe more. I mean, you'll see it's very easy. The second claim is an analytic claim, which is that this Hessian has exactly one positive eigenvalue. Okay, so it's a symmetric matrix. We're claiming that it has exactly one positive eigenvalue. This also goes back to at least Alexandrov. So I'll prove these in a moment, but any questions about these claims?
So not a question about the claim, but I think I'm like a little lost about how you defined V of C. Like what is C0?
Right, so V of C0 is the volume of P polar. So what I'm doing is I'm going to replace the C naught by a variable C, right? And as I change C, I get different polytopes, right? And each of them has a volume. So that defines a function. Does that answer the question?
And then when you take the Hessian of this function?
Yeah, you take the Hessian of that function V. So V is a function, right? V is a function from Rn. Well, okay, I didn't define it everywhere, but sure, I can define it everywhere from Rn to R. Right? Because for every C I put in there, I get a polytope and it has a volume. I mean, okay, I don't want to define it on all of Rn because the volume could be infinity, but volume is continuous, and in a neighborhood of this C naught, these will be finite. So this is a well-defined function in a neighborhood of C naught.
Okay, I see, makes sense.
And then I can take derivatives, right? Yeah. Any other question?
So the Hessian should have all non-negative entries, right?
Well, you mean in order to apply theorem S?
Yeah, that's one thing. But I guess my intuition is like you increase C, one entry, two entries C at the same time. There's it's like the Alexandrov kind of argument.
Yeah.
Where like you add a square term in the volume, right?
Your intuition is absolutely correct. All the off-diagonal entries are non-negative, as we'll see on the next slide. The diagonal entries are negative, but yeah.
Okay, yeah. I was thinking off-diagonal. Yeah.
You're right. So let's now see this. So claim one, this is a generalized adjacency matrix. So let's just compute the derivatives, right? So let's draw two facets, Fi and Fj of P polar, and let's perturb the ith slack entry, right? Ci. when that happens, that facet is going to move a little bit. And it's easy to see the change in volume is going to be the, well, d minus 1 dimensional volume of that facet. Okay, from this picture, right? If you slide the ith constraint a little bit, then you're going to move parallel to the facet fi, and the change in volume is going to be proportional to the area of that facet, which is I've written as absolute value of fi. So the first derivative is kind of clear. And now if you want to calculate the second derivative, you need to do a little trigonometry. But I mean, I won't go through it here, but it's a sort of trigonometric exercise that now you're interested. The second derivative, the partial I partial j, is asking how much does the area of fi change when I move fj, right? That's what it's asking. So the angle is obviously going to play a role. And if you just work this out, you get that it's this. It's the d minus 2 dimensional volume of the intersection fi intersect fj times cosecant of this angle. And by the way, this angle is not 0 because there are no redundant constraints. So, I won't do the trigonometry, but the point is this is not 0 if and only if two facets are adjacent. And indeed, this is positive, as Greg said, for adjacent facets. So that's the proof of claim 1. It's just calculus. Any questions about that? Okay. Proof of claim 2, that the Hessian has exactly one positive eigenvalue. This follows from the Brun-Minkowski inequality. So this function C goes to log of the volume of C. So you can now take the log, right? Because the volume is positive, at least in a neighborhood of C naught. It's a fact from convex geometry that this is a concave function. Okay, so this is equivalent, essentially follows from or equivalent to the Brun-Minkowski inequality, which says that log of volume is concave under Minkowski addition. I'm not claiming this is obvious, but it's a classical inequality in analysis. And a different phrasing of it is, I mean, okay, what's written in the parentheses is literally the same after exponentiating, but you may be more familiar with that version of the Brun-Minkowski inequality for polytopes. Okay, so this is an analytic property of this function, that its log is concave. But now, okay, this means that the Hessian of the log of v is not negative semi-definite, and then by calculus, which is just a general fact about functions, the Hessian of the function itself has one positive eigenvalue. So this therefore stuff at the bottom is just chain rule or whatever. But the point is it's a concave function. So any questions about that? Okay. Now it sounds like we're heading in the right direction, right? We have a generalized adjacency matrix. We know something about its eigenvalues, namely that exactly one of them is positive. But really, we need a spectral gap, right? We need a quantitative bound. So how do we do that? So that will be claim 3, which is just a little observation. The observation is that this Hessian, if you actually calculate it, has an additional useful structure, which is it's equal to negative a graph Laplacian plus a diagonal matrix. Okay, if you know what a graph Laplacian is, it's a special kind of adjacency matrix of a graph. And the important property of a graph Laplacian is positive semi-definite. Okay, so if you just write out what the entries of this Hessian are, you will observe that it's equal to negative a graph Laplacian plus a positive diagonal matrix. So this is sometimes called a Schrodinger operator in, I guess, physics. Now, once you have this, it's kind of nice because you can turn that qualitative statement about one positive eigenvalue into a quantitative statement about spectral gap by doing the following. Consider the matrix d to the minus half h d to the minus half, where h is the Hessian. So you rescale the matrix by the inverse square root of this diagonal matrix on both sides. So we can do that, right? The equation in claim 3, if we rescale by d to the minus half on both sides, you get that this rescale matrix is minus d to the minus half L d to the minus half plus identity. Okay, so now we're happy, right? Because the matrix on the left-hand side has one positive eigenvalue by Sylvester's law of inertia. You didn't change the signature by multiplying on the left and right by diagonal matrix like that. By the same argument, the first term on the right-hand side is negative semi-definite by Sylvester's law of inertia, because the Laplacian is positive semi-definite, so minus the Laplacian is negative semi-definite. And so when you scale it, that doesn't change. So you have a matrix with one positive eigenvalue equal to a negative semi-definite matrix plus identity. So the only way that's possible is that the top eigenvalue is equal to 1. And so we conclude that this scaled matrix has a spectral gap of 1. Okay. This is not a deep thing, but the structure, Schrodinger structure, is important to be able to do this. So any questions about this? Okay, so we're almost getting there to be able to apply theorem S, but we're not done because this thing has a spectral gap, but we don't know where all the other eigenvalues are, right? They could be all over the place. They could be very negative. They could be whatever, right? So really the punchline is that after doing some calculations and some matrix analysis, you see that a certain affine scaling of this matrix actually has all the properties you need for theorem S. Okay, it's a adjacency matrix of the graph. It has a strictly positive eigenvector, which we saw in the last part is required. It has a spectral gap of gamma, and all the other eigenvalues are contained in the unit interval. And this gamma that you get after you do these calculations, which I'm skipping, are that the spectral gap is equal to sine squared of the minimum angle between facets of the polar. So it's a measure of non-degeneracy, right? So if you go back to this picture in this little proof here, I had these angles theta ij, right? And as the polytope is getting degenerate, they're getting very close to 0. So when the dust settles, when you do all this stuff, you get that the spectral gap is the sine squared of that angle. So it's some measure of degeneracy of the polytope. And now you can apply the theorem, right? You have an adjacency matrix of the graph you care about. It has a spectral gap. The eigenvector is positive. And so you get this bound. The diameter is bounded by log n plus 2 log 1 over v min over sine theta. And then you have to do some more work to relate this theta min and v min to the integer entries appearing in the matrix, which I'm suppressing because it's just a bunch of calculations. But the point is that you can control both the angle between facets of the polar and the entries of the top eigenvector of this matrix, which are positive. You can control their magnitude using this fact about the integerness of the matrix, right? So you can prove that because they're integers, these things can't be 0, and there's some bound on how small they can be, and you just calculate that bound, and then you get the result. And okay, final green parentheses. I assumed all this stuff. I assumed the polytope was simple. And even in defining the Hessian, you can remove this assumption by an approximation argument, which is due to Ismetsiev from 2010. So the simplicity does not pose any serious concern. So that is the proof of the theorem. This is a summary of what happened, right? You pass from P to P polar. You look at log of volume. I guess it's volume of, volume of what? It's volume of P polar of C as a function of the slacks, right? Just to remind you. And the analytic fact is that that's concave. That tells you that the Hessian has one positive eigenvalue, which then, because of this Schrodinger structure, tells you that a certain scaling has a spectral gap, which then this is where you apply theorem S. And you apply this stuff about knowing the integer entries, you get that the skeleton has small diameter. So that's an outline of the proof. And the goal was to just present this idea of using log concavity to get a spectral gap. In the paper, we use this to prove something a little more intricate, which is not on the slides, but well, okay. We analyzed what happens for random polytopes and proved that their skeleta, which are random graphs, have a giant component of polynomial diameter, if that is interesting to you. But I guess the point is that this idea can be used to prove, more other statements beyond just this integer polytope small diameter. So that's a summary, and here are some open questions. So one is, can you prove the polynomial Hirsch conjecture for random polytopes using this technique or otherwise? I mean, using whatever technique you want. Another question is, can you analyze a natural random walk on the vertices of the polytope using, so in this talk, we use continuous log concavity, which is literally log concavity of the volume. But there's this very important work of Anari, Vescaran, Liu, and Vincent, where they analyzed random walks on matroids using a certain notion of discrete log concavity. So one speculative question is, can you use techniques like that to analyze any random walk on the vertices of a polytope? It's not too far-fetched, but we weren't able to figure it out. And a final very speculative comment is that this one positive eigenvalue is part of something called the Hodge-Riemann relations associated with some graded algebra associated with the polytope. And speculative question, are the other ones useful for doing combinatorics of this sort? So that's it. And I don't know why my video stopped working, but yeah.
Let's all thank Nikhil. Some clap emojis. And we have quite a bit of time for questions. So if anyone has any questions, the recording is off now. So